Hello, everyone. It's great to have you back for one of our presentations for the Spanish-speaking acousticians in the Americas. We are pretty excited. We have a very, very special guest, and as you know, always we have been sharing extremely interesting contents with very, very special guests, uh, especially this time that we have Professor Trevor Cox, and sharing a very unique presentation for his research, which is extremely interesting. And I want to do, first of all, a short introduction, although I'm sure that a lot of you know very well Professor Trevor Cox. So Professor Trevor Cox currently is Professor of Acoustics Engineering at the University of Salford. He is the past president of the UK's Institute of Acoustics, and he has been very well known for his research in acoustic diffusers. His current research projects are about hearing aids for music and speech, and he has presented many documentaries for BBC Radio, including The Physicist's Guide to the Orchestra. He won an ASA Science Writing Award for his popular science book Sonic Wonderland, and the book describes the oil tank where he broke the Guinness World Record for the longest echo, among several other remarks that we know from him. I'm sure that all of us have read articles or books that has been written by Professor Trevor Cox, and we are very, very excited to have him here just right now for his presentation, using scale modeling to assess the prehistoric acoustics of the Stonehenge. So thank you, Professor. It's great to have you here, and I think people want to hear you and not me. So it would be great that you start with the presentation. And once again, thank you for sharing with us.
Hi there, everyone. And I hope I'm coming through okay, because I had a webcam issue just 2 seconds ago, but I think I'm all right. And thanks for the introduction, Andres. As people kind of who know my research kind of know quite a lot about my research into diffusers. And funnily enough, quite a lot of that work kind of comes across into this particular project, which is about looking at this prehistoric site, Stonehenge. Well, it's fairly world famous, but I'll introduce it. And if you're really interested in this work, we wrote it up for an article, and I'm sure you can find it in the Journal of Archaeological Science. And what I want to do today is kind of go through and sort of kind of talk about what we did and why and what we found from this study. So if you take something like Stonehenge or any of these prehistoric sites, we're before there's any writing. So we don't know exactly what people did there, and we have to rely on archaeological evidence to look at what they might have done. And if you take somewhere like Stonehenge, which is this grand site, which was a tremendous amount of work to construct, no doubt there were rituals going on at this, whether it's, I don't know, celebrating the living, the dead, or whatever it may be. There were rituals. And if we think about human rituals, then they involve sound, whether that's going to a church service to sing, or turning up to some christening, or going to some wedding, whatever it may be. You have people speaking, you have music being made. So we can expect sound to be being made in Stonehenge in its prehistoric days. And we all know, because we're acousticians, that the sound of space actually influences how you use it. And so understanding the acoustics of Stonehenge helps us to understand a bit more about how it might have been used. If you go to Stonehenge nowadays, this is what it looks like from a drone picture. And I was actually there not that long ago. And you'll see that quite a lot of the stones are actually missing from what was potentially there. You'll see there's quite a lot of tops of stones that are kind of missing. And so people often ask me, why don't you go and measure the current site to find out what the ancient acoustics were? But the thing is, the ancient acoustics would have been very different if all the stones had been present. About a third of them are missing or fallen over. So that's the reason we don't go and look at the current one. And then you start thinking about kind of how could we recreate the acoustics of the past. And one of the motivations here was actually someone did some computer modeling on Stonehenge and produced results that, just drawing on simple physics and what I know from diffusers, seemed fairly unlikely the results were correct. So this is from a paper where someone said, okay, what we have in Stonehenge, you look on the right-hand side, is we have this circular outer ring. And if you have a curved surface, of course, you get focusing. And so you start thinking, okay, there's going to be a focal point where we might get an echo right in the middle of Stonehenge. And they drew this picture up on the left-hand side, so, oh, there's an echo going on. And then they produced, using a fairly well-known geometric room acoustic model that some of you have probably used, they produced this kind of picture, which seems to show for the impulse response direct sound and some very clear reflections. And you think, oh, well, maybe there's an echo, and that's what the paper outlined. The only problem they didn't seem to realise is these reflections arrive far too early. And actually, they're from stones from within the stone circle. They're not from the outer circle. So they got the timing wrong of them. And the thing is, this is a geometric room acoustic model, which is a high frequency approximation. When we look at the Stonehenge stones, they're very knobbly, and they're not like simple flat reflectors. So there was a mistake made in this paper about timing, but also an assumption that a geometric model would produce accurate results. But unfortunately, this is a particular space that is very difficult to model with something like ray tracing or image source. And to show you why there's no focusing, just to complete this picture here. So this is my model. So if you imagine going back to Stonehenge in 2500 BC, this is kind of approximately what it might have looked like. So we're looking through from what's called an inner trilithon. So a trilithon is these uprights. Sorry, we're on the edge of the circle here. A trilithon is these uprights with this lintel on the top. And this focusing circle is this thing you can see towards the back. And what you can immediately think is, you think your sound going to this circle and coming back again. Well, most of the paths to this circle and these ones at the back and back again are actually obscured by all these other stones that are in the way. And that's the reason you don't get focusing in Stonehenge, is because there's too many stones in the middle for the sound to very easily get to the outer ring and back again. And each of these are, I guess I would call them diffusers if I want to cite my original research. And although these look quite small, you might think they're quite small. You've got to bear in mind these are almost 1.5 to 2 meters tall. So some of these are head height. These big ones are really big. You know, they really tower over you if you go and stand in the site, 4 meters tall or something like that. So when you look at so here's an impulse response, and here's my scale model. And I'll go through how we measured it and everything in a moment. I'll put it in dB. And if we were looking for reflections from that outer circle, we would expect to see something around here, which looks like some sort of focus, a big peak here. And as you can see in this physical scale model, there is nothing in this impulse response that makes you think, oh, there's some reflection which is focused and very strong and should cause an echo, because there's so much scattering on here. It's a very diffuse field because of that. We'll also talk today a little bit about what's called the Maryhill replica. So computer modeling isn't a very good way of doing this, because computer models currently don't work very well for this sort of space. You could use finite difference time domain, but it's a very large space, so it would run for a very long time. The other possibility is go and measure a replica, and there's a few around, and the Maryhill one's across in America. It's in Washington State, vaguely near Seattle. And that's not a bad replica of Stonehenge. And I've just put in here the impulse response. It's a one-to-one scale model. It's a full scale thing. We'll see a picture of it. And again, this is where you'd expect potentially there to be echoes from reflections from the outer Sarsen circle. And although you can see there's some louder reflections, they're not of the scale that would be expected to create something like an echo effect in the room. And just finishing this echo story before I go into how we made the model. Here is actually on the left is my scale model. You're looking in the center where the focal point is. You're seeing this outer Sarsen circle in one direction. This is the Maryhill monument. And you can see, it looks kind of similar, but you can also start to see differences as well between these two. So for example, these, what are called the blue stones. So the little stones are called blue stones, and they come from Wales. So they come from a very long way away. I'm not sure how far it would be, 100 kilometers away, maybe. from where Stonehenge actually is. So these ones are transported a long way. You can see they're very perfect in this Mary Hill thing, nice little square rectangles, whereas real rocks coming out of quarries are much, much more knobbly. And so are not as such good at scattering. And there's many, as reflecting purely. And there's also many more of them getting in the way of the sound bouncing off this outer Sarsen circle as well, compared to here. So that's the reason we measured this model partly, because we have measurements that this Mary Hill monument was made by Rupert Till and Bruno Fazenda, and you can look a paper up by there, but it's too perfect. It's not quite what Stonehenge used to be like. So that's the motivation behind the modelling, was first of all, people were publishing papers with geometric models which were wrong. And the second motivation was to try and understand what was going on. And it kind of struck me, because I come from architectural acoustics, that we had a technique in architectural acoustics that had never been applied to a prehistoric site before. So this is Mike Barron, and he's so Mike Barron, you might have seen his book, he's now well and truly retired, but was obviously famous for doing lateral reflections back in the 70s. And he is sat in a 1 to 8 scale model of the Barbican Concert Hall in London. So this is a technique that's the idea of building something, a replica scale model, is something that has been around probably since about the 1930s in room acoustics. It is not used very often nowadays because computer models are usually accurate enough and they're a lot easier to do than to build something like this. Yeah, so it's a technique that I could sort of kind of take the technique previously used and apply it to a prehistoric model. And this was the first time someone had tried to do it. Now, the first decision you want to make whenever doing scale modeling is how big do you make the scale? So I ended up with a 1 to 12 scale model, and I have a picture from Spinal Tap here. And for all those fans of Spinal Tap, yes, it's the same scale that they had. Because normally when I do a talk, someone's got to mention Spinal Tap, so I thought I'd be first. But if that means nothing to you, forget the comment. But anyway, it was 1 to 12 scale. And the reason that was is we had to fit it in our semi-anechoic chamber. And that was the size which meant we could build it and fit it in. So it was kind of coincidence it was 1 to 12. You make them as big as you can, because if you shrink things down by a size of 12, you've got to go up in frequency by a factor of 12. And the reason you want to do that is so the wavelength of sound in the model compared to the size of the stones is the same as it would be in real life. So because the stones are 12 smaller, you need to make the wavelength of the sound a 12 smaller. And so you end up with going at 12 times the frequency. And that means you start off testing, we were testing from 1,000 hertz up to about 70,000 hertz. So you start off with something you can hear and then go into ultrasonic frequencies. Now, the reason you don't go to higher frequencies than that, if you can get away with it, is a couple of factors, but one of which is air absorption. So when we model or measure, say, a concert hall, the absorption of sound goes through the air is not normally the most important absorption. The most important absorption is when the sound reflects off objects, like off the seating. But in big spaces, it becomes more important, and at high frequency, it becomes more important. So the air absorption at 12 times the frequency is different. So if I have real full-scale air absorption at 1,000 hertz, it's very different to the air absorption in the model at 12,000 hertz. And that's because the air absorption is non-linear and it's determined by various factors. So by making the model as big as possible, you have a smallest scale factor you can get away with. And that means the air absorption correction, or how you have to deal with it, is a bit easier. So you tend to make these models as big as possible. In consoles, they go down to about 1 to 50. They're really going smaller than that. You also have to scale the material. So I get often asked by people about, on this model, if you look at pictures of the model, you'll see it again in a moment, the model is actually on a wooden floor. And they say, well, why isn't it on grass? And that's because the absorption in the model of the floor at 12,000 hertz has to be exactly the same absorption as grass in Stonehenge real at 1,000 hertz. And so you don't use the same materials. You're trying to match absorption coefficients and properties at a 12 times sort of frequency factor. Now, that's actually really easy to do for the stones because they're very reflective, and most of the absorption comes from sound going from between the gaps. So actually getting the stone material right is actually relatively easy. The grass is a bit more problematic. So again, that's another factor we know about modelling. And the final factor, if you're ever doing scale modeling, which is a real pain, is loudspeakers and microphones, the transducers. And it's odd really, because there's no real reason why we couldn't have more transducers that work across this frequency range, broadband. It's just no one really makes them. And therefore we end up in this situation where we don't particularly have transducers readily available, which is kind of a bit of a pain. So yeah, there's a picture of the 1 to 12 scale model, and you can see it's actually on wooden flooring. It's unvarnished MDF, and that's to try to kind of match up the absorption of the floor with the absorption in between model and real scale. You can just about see the transducers. It's quite hard to see this. You might be on a computer screen, it's quite small, but that's a 1/4 inch mic. So getting a microphone to work at high frequency is fairly okay, but these are fairly insensitive microphones. They're not really, they go up to ultrasound frequencies that kind of were designed really to deal with very high intensity levels rather than to be very sensitive. So they're a problem because they have a lot of electrical noise. And now I'm holding one of the sources we use, which is a little super tweeter by B&W, little super tweeter there to cover the high frequencies. So how do we go about making this kind of model? So I'm not an archaeologist, so the first thing which is really important to me is I need to make sure that the archaeology is done correctly. So we worked with someone from English Heritage. So English Heritage is one of the people who look after the site. And there's also a group called Historic England. They are different, but they're very related. And they had done work on reconstructing what Stonehenge would have been like in the past. So we took their reconstruction model. So they sent me this CAD model of Stonehenge. Because when we talk about Stonehenge, it actually was in different configurations. I'm talking about this one, where there was the most numbers of stones, and it's about 2,200 BC. So it's about 4,000 years old. But it started off with a more simple stone circle, about 2,900 BC. So it's been in different configurations over time. I'll come back to that. So they gave me this computer reconstruction, which is where I started with. And then you start thinking about, well, how am I going to make them? How am I going to physically make these things? So the first thing you might think about is to get out a 3D printer. And here we go. Here's 3D printing one of the blue stones. So this is one of the smaller ones. So when these are printed out, this is, I don't know how tall this one is. It might be like 10 centimeters tall, maybe, that kind of size. And so some of the stones are printed in 3D. We need to make sure they're not going to absorb any sounds and look like rock. So actually we printed empty ones and filled the back of them with concrete. So they're really quite heavy. And then we painted them to make sure the surface of the model was completely sealed. So we painted them as well. But we started off with the idea of 3D printing them. But they take a huge amount of time to print. So the really big ones, this is a really big 3D printer. That one there, which is what the tallest trilithon, so that's one of the tallest uprights in the middle, it took many days to print, and we worked out we just couldn't do it. We just couldn't print enough of them in time. It would take sort of so many months. So we went for a slightly different way of making some of them. So what we did is we looked at these, for example, all the little blue stones, the little ones in the middle, and we kind of go, well, look, if you look at them, they kind of cluster. So there's some which are sort of short and fat. There's some which are narrow and tall, and they've all got some kind of different sort of generic sizes. So what we did is rather than print individually all these different sizes, we picked one which was representative of this kind of shape, and we printed that, and then we molded replicas. So if you look in our model, you'll see there's replica stones. Because they're randomly orientated, it won't really matter too much to the acoustics, because of course acoustics is about thousands of reflections. And this is a way we could therefore make it, because it's much quicker to mold things. So we clustered them together based on their shape and size, and then basically printed one from each of these clusters. Was a way of reducing the number of amount of printing we were doing. And so you can see replicas in them. Let's see if I can spot one here for you to look at. So for example, if you look at this stone here, there's a little dimple here you can see here. And if you go around on the side, you'll see, oh, look, this is the same stone over here. So there was, if you look at, start staring at them, this stone is the same as that stone. One's turned around compared to the other. There are some duplicates because of the problem of making lots of them. So I actually spent a lot of time learning about molding and modeling techniques, so what you do is you 3D print the one you're going to mold. And so this is about 30 centimeters high, it's quite tall. You then make a silicon mold, around it. So you then have a silicon mold, and then you tip the material in there, and then you can make as many as you want. And so most of them are made out of a plaster polymer mix. It's a very hard but durable mix, and then we paint them afterwards. And this became quite a project because basically I had no resource to do this. This was all done in my spare time. So this is a picture of my dining room at home, where I did a lot of the modelling in my evening as a hobby. I made most of the stuff at night. And then we got the problem of how do we set the stones out? Where do you put them? And we came up with this idea of using a CNC machine to mark out these big boards. So we took the CAD model and put a cross on where every stone had to be, and then we drew out on these ginormous MDF boards where every stone had to be kind of put into the system. So we have these very large boards which are actually showing you how to lay out the stones in the right place. And that's what it looks like when it's in the semi-anechoic with the boards. And then here's some time-lapse photography of me actually putting the stones in with my colleague Josh. So it takes a few hours to put up. The really slow and tedious thing, which isn't that obvious because this was for a picture rather than proper acoustics, is you have to seal around all the cracks. So everywhere where there's a gap potentially between the stones, then you have to get plasticine in there and fill in all the gaps to make sure there's no little cracks that might cause excessive absorption. Because in the real Stonehenge, they're really well jointed, and they're not quite so well jointed in my model. But you can see here's the different stones. So this big ring I've been talking about for focusing effects is called the outer sarsen circle. The little ones are all called the blue stones. These are the inner trilithons, and this is called the altar stone, which may or may not have been altar. It may have just been a stone that's fallen over. We put it in the semi-anechoic because basically, if you look around Stonehenge in where it's based, which is in the south of Britain, in Wiltshire, there's basically just not very much around it. So this kind of simulates the effect of when sound goes out the ring, there's nothing to reflect off to send it back in again. So it just gets absorbed by the wedges. And of course, this is essentially an experiment in still conditions, which is kind of the conditions we're dealing with. Of course, in real Wiltshire, there could be wind, there could be refraction due to temperature inversions. Well, we didn't model that. So here's the transducers. As I said, the little microphones are insensitive, but that's a standard sort of grass or B&K quarter-inch microphone. And here's my little omnidirectional source, or horizontally omnidirectional source, made out of little ring tweeters. And although it's meant to be omnidirectional, it isn't entirely, but if you look at the paper, there's a bit more detail on how to make this stuff. But it is a real pain because the transducers, in theory, you should be able to get much better ones, but no one makes them. So they're all kind of a bit of pain to get hold of what you use. So when we go and measure this, I assume some of you are room acoustics, but for those who aren't in it, what you do is use a sine sweep. So we're going to sweep from 1000 hertz to 68 kilohertz. And then we're going to use a deconvolution with the inverse of the sine sweep, which is an absolute standard technique for measuring in room acoustics nowadays. It's enshrined in standards. The one sort of complication that you have when you're doing this with Stonehenge is that the microphones, you can't get very loud noise out of the transducers. There's lots of gaps between the stones. So actually the reflected sound isn't very loud. And then the microphones are noisy at high frequency. So whereas if you went into a concert hall and made a measurement, you might just run one long sine sweep and you're done. To get the signal to noise ratio we needed, we had to average over 128 sine sweeps to reduce the electrical noise on the microphone. So it's quite a tedious kind of process. But you can see here, so red is the background noise, blue is the sine sweep. You can see that we have at low frequency quite a very good signal to noise ratio, less at high frequency, but we get away with it because we average over an octave, and that then gives us a better signal to noise ratio. And here we've got a decay. So this is an envelope decay of the impulse response over time. And you can quite clearly see we've got a sort of kind of nice length of decay. You know, you talk about RT, you want to be 60 dB. You can get quite reasonable background noise level measurements in the space. But it's a tricky one to measure. A concert hall's a bit easier because it's got a higher reverberant sound energy than this model. So where do you measure? That was the next problem we had. You've got this scale model. Where do you put the source and receiver positions? Because if you look at standards, it will say, okay, put the source on the stage, put the microphones in the audience. Well, we have no idea where people were stood. There's no evidence on that. So we did lots of source positions. So the squares are all the source positions, and green, you can see lots of different ones. The red ones, the dots, are all the microphone positions, and we just did lots of those. We did some inside the circles, some outside, and we basically chose them thinking about acoustics. So we had some where the microphone to the source, you couldn't see the source. So if you're at this microphone, if you're in this source S4, you're stood behind a really big stone and you can't be seen from microphone 22. So that'd be a blocked path. Whereas if you were, say, its source was in here and your microphone's at 22, there's an unobtrusive line of sight. So line of sight was something we looked at as well. But those are some of the positions we chose, which, to be honest, were based on sort of thinking about what might change and were pretty random, to be honest. And here's the results of the reverberation time. The decay time it takes the sound to decay by 60 decibels over frequency. And so the dotted one here is the original, or is the current Stonehenge, which, as you saw, I said stones are missing. It doesn't really have reverberation. I mean, you can measure reverberation time at 0.3 seconds, but it's not really very reverberant. The blue one is the measurement in Stonehenge. Because model, so in my model, because there's so many stones, it's actually quite diffuse. So that's an average over 29 microphone positions. So that's the reason the error bars are so small, because the reverberation time doesn't vary very much around the space. And the other one, the red one, is from that Mary Hill replica, the American one I show you, which was a bit too perfect. So what does this reverberation time mean? Well, 0.7 seconds. It's a big space. I haven't said how big it is. It's about 30 meters across, so it's a very large space. It's probably the nearest modern equivalent I can think of would be a cinema. If you go into a big cinema, there's a lot of absorption around because most of the sound's coming from the loudspeakers. So if you talk in a cinema, not through the loudspeakers, but chat in a cinema, it's big, but a relatively low reverberation time. And that's basically what it's like. And if we think about 0.6, 0.67 seconds, it's going to help a bit with speech, but not as much if it was a bit more. With music, again, it will help a bit with music, but bigger values are probably a bit more optimal. But that's I think the fact you have any reverberation is quite surprising, because if you look at the model itself, let's go back to one here. So there's lots of holes here between the rocks where the sound will just disappear. There's no roof on the top. So it's quite surprising at all that there's a reverberation. And that's because the sound can keep in the horizontal plane. It's basically what's happening. It's rattling back and forward horizontally. It's where you're getting this decay at all. So to me, it's quite surprising it's got a decay time to it. It's about 0.7 seconds. Early decay time is a bit more relevant to what we hear in reverberation. So reverberation over 60 decibels, you don't often hear the whole 60 decibel drop if you're, say, speaking or listening to music, unless you're at the end of a sentence or at the end of a piece. So the EDT, which is over the first 10 decibels of decay, is a better measure, usually of reverberance. These are just different positions and showing there's different characteristics. So the green one here is actually when the source and receiver are near the center of the model and are close together. And actually what you're really measuring here is the decay of the measurement protocol, because it's so there's not really much happening from the stones. It's more the direct sounds. You're measuring the sort of decay of the transducers. You're also seeing some of the problems of EDT because of the cutoff at 10 dB. Depending on where reflections arrive, you get these sort of kind of slightly anomalous results with EDT, which is expected. So I'm not going to talk about the green ones because it's not, when you're close to the source, the decay time is not really that relevant. The blue and the red are a bit more interesting. So these are two different source and receiver kind of characteristics. So they're a group of ones. And basically there's a difference between whether you can see from the source to the receiver or whether you can't. Do you have a line of sight?
Trevor, may I interrupt you? I'm sorry, I think we lost your audio. And your image also seems to be frozen.
Is that doing any better?
Okay, that's better. You're back.
I apologize for this. Where should I go back? When did you lose me?
Just a couple of seconds, not that much.
Oh, okay. Yeah, I'm sorry. I don't know. The intermittent fault on the webcam. Never happened before. Really annoying. Yeah, so when you've got the block line of sight, you lose this direct sound, and therefore the early decay time extends. That's what kind of this kind of plot is showing. So line of sight is important to performance in what it's like in the space. So we then sort back, well, what's going on in the space and what can we learn from it? So the first thing we might think about is speech. So 2200 BC, definitely speech was happening. We don't know what was exactly said because the sound disappears, but we know, humans started to talk. I mean, you can guess about the sort of kind of exactly when, but 500,000 years ago might be a good first guess. So we start trying to work out, well, how did these stones and the reflection of the stones help speech within the space? Does it help with speech intelligibility? So the two unknowns, which make it very difficult to answer this question, is first of all, we don't know how loud the background noise was. So when we had a ceremony going on, was everyone silent, or was everyone talking when those ceremonies were going on? I mean, there's go to a party and it's really buzzy and noisy, isn't it? Go to a Quaker meeting, it's really quiet. So it's quite hard to know how loud the background noise was. So that makes it hard to judge intelligibility. And also, was intelligibility important? So there's times in certain religious ceremonies where intelligibility isn't important. And a good example of that would be pre-Reformation church services where everything was delivered in Latin. So did it really matter what they were saying because no one understood it? So there's some unknowns here, but it's assuming that speech intelligibility was important, assuming that people were relatively silent, we can have a look at what speech intelligibility was like. So we looked at D50, which is the early first 50 milliseconds energy compared to the rest of the energy. It's a standard measure. And basically, D above 0.5 is pretty intelligible. And that's kind of what we find when we look at it. We find it's about 4 dB louder with the reflections of the stone. So it's a bit of gain, makes it a bit louder. And where that would have made a difference is probably if you were talking in that circle, but you were a long way away and maybe you weren't facing the person listening to you, there's lots of reflections to help amplify the sound. It's a bit like being on the stage of a theatre where you've got a stage set, which is helping you to amplify sound. It's a bit like that kind of thing. So that's where it's really noticeably useful. But, in some cases, if you're close in the middle of the circle, the stones are not that important. It's probably over larger distances where it becomes more important. Anyway, I thought I'd play you an auralization of the space. So I did various press things around this. You can imagine the press were quite interested. And so I've got a short extract from a Radio 4 presentation where you'll hear me talking and it's just a radio recording. And then we add on the effect of Stonehenge. So you suddenly hear the effect of the stones. Hopefully down the Zoom line, you can hear the difference. It's like listening to someone talking in the bedroom and walking to the bathroom. The timbre is going to change, the volume changes a bit. And you should have a sense of stones appearing.
You're hearing my voice recorded in an anechoic chamber. There are no reflections. All you're hearing is the sound straight from my voice to the microphone.
And here I am in the model of Stonehenge, an auralization of what I would sound like if I went back to 2200 BC and talked within the monument. So hopefully that's good enough down the Zoom line to hear the timbre change, slight change in level. And yeah, which is what you'd kind of expect. I mean, what's interesting about this is we think about that change in timbre and think about how that's really normal. That's like me going into my garden and then walking to the kitchen. We hear these sort of changes all the time. We kind of ignore them really nowadays. But actually, if you go back to 2000, 3000 BC, there weren't stone buildings. So this sort of kind of acoustics would have been much more unusual. Where you would have met it would maybe in caves, in gorges, and there are a few around Wiltshire, not that far away, caves and stuff. So they would have heard it naturally, but in a man-made construction would have been quite unusual. So speech is improved inside the circle, but it's not. One thing we're more interested in is what happens when you look from inside to outside the circle. So we had these microphone positions outside, and basically if your makers, I think it was this central source, the sound is attenuated by 3 or 7 dB as it passes through, depending on which of these microphones you look at. So if you wanted to hold a conversation in this space, it's much better if everyone is inside this outer sarsen circle. And that's kind of the interesting sort of archaeological thing, because you can start saying, well, if people are trying to communicate within the circle or in this site, then it's better off if they all get inside the circle. And it starts to get you thinking about how they might have used this space. I say 3 or 7 dB because it really depends on whether there's line of sight or not, how much the attenuation is, again, as it was elsewhere. And just a couple more points. I'm just going to talk about the different stages of Stonehenge and then also what I've been doing lately. So as I said, Stonehenge was in different forms. We thought it'd be interesting to see how important different parts of the model were to try and understand how the different forms of Stonehenge changed. By forms, I mean this outer sarsen circle wasn't there at the start. These blue stones were not in these positions at the start. There were different things going on. So what we did is we measured this model, then we took out all these top stones and measured it again. Then we took out all the little stones and measured it again, and just saw how the acoustics varied. And I'm going to show you the plots, the reverberation time, as we go to different constructions. So what we have down here is the acoustic when we've just got these big stones that are in the middle. They're called the inner trilithon horseshoe. So it's these big 2 uprights and 1 top thing that you can see in the middle there. And you can see the reverberation time is pretty low. It's about 0.4 seconds. As soon as you add this big circle of stones around the outside, then you suddenly get a trapped sound, and you suddenly get this reverberation kind of doubling. And that's where you get the sound bouncing back and forth much more efficiently. And so you start basically seeing the effect of that. So the big difference when they were building different configurations was when they completed the circle. Now you can have a debate with archaeologists about whether they ever did complete the circle. It's assumed they did, but still the evidence is incomplete for that. And then all these different lines, which I won't go into detail, but they're playing around with having the blue stones in and out. And you can see it doesn't make very much difference. It's really those big uprights in a circle, which makes the big difference to the acoustics, the reverberation time in this case. So what's the next steps? Well, this has actually happened, but unfortunately my life has got so busy I haven't had time to analyse the results yet. But we've actually done some measurements with occupancy. So one of the things, if you've ever looked at scale modelling in consoles, is they also model it with little people in it. And here is a scale model person. This is my scale model person. So you've got to model the clothing effect and scale it to 1 to 12, so it's a bit of a pain to make. But I made 100 little people, I put them in the model, I've measured them with and without the model. I'm afraid I haven't had time to look at the results because my life has been too busy. The other thing I did at the same time is this measurement has been monaural. So the measures I've presented, reverberation time, early decay time, D50, are all monaural. Of course, we have 2 ears. That makes quite a difference. And so we also measured with a microphone array, and I made a little shrinking microphone array as well. I measured to higher frequency to allow for better auralization. I want to release an impulse response for people to be able to do what I did in that auralization demonstration. But when I made that, I had to cheat a bit because we didn't go up to high enough frequency. So those 3 things have actually done, but not actually been processed yet. And then the next 2 bits we're looking at is computer modeling. So I talked about geometric models being not the right thing, but there are finite difference time domain models or boundary element models which would work. I just need to sort of kind of get around to running some modeling on that, because you can get them to run fast enough. It's just a very slow job. You need a big computer. And the other thing which I've done a little bit of work on, I haven't had time to write up yet, is that those blue stones, which I said travelled, I'm guessing 100 kilometres away, I'd have to check that number, but it's a very long way away, were originally in a different stone circle in Wales. And they've got evidence of what the stone circle was. So I'm hoping to model, again, it has to be a computer or might be a scale model, the original blue stone circle, the original Stonehenge, which was in Wales. And I've got a student who did that in a computer model. It looks really interesting. Just need to find some time to write it up. So if you've enjoyed that, you can go and find the article if you want to read about all the different, all the details there. And I hope you've kind of found it interesting. It's been an amazing project, a really fun project to do. if you do anything with Stonehenge, you immediately get lots of interest, lots of press interest, which I didn't kind of quite imagine. But it's, you know, it's really, I'd encourage people to get involved in archaeoacoustics, partly because some of the work being done lacks acoustics rigor. So we need more acoustics experts involved, so we have the rigorous and correct acoustics being done into the future. So thank you very much.
Thank you, Trevor. That was great. That was a lot of information, very interesting information. We have a few questions in the Q&A option. Jack actually said he's doing research in a similar topic. First question, I'm going to read the first one first. How did you solve the transducer limitation, especially regarding the loudspeaker signal to noise ratio?
So to be honest, just by averaging a long time. So the limitation, even though we're in a semi-anechoic chamber, the limitation on the microphone was its electrical background noise. So if you sit and average a long time, the electrical noise is random, and the acoustics doesn't vary. And so therefore you can basically average out the electrical noise. The other thing to do is to try and get louder transducers. It's a problem because our model's slightly open. You know, there's all those gaps that actually you don't get very large reflective energy. And there's ways around that, but the problem is you get more powerful transducers that are too big, physically too big, so you put them in the model, they affect the acoustics. There are techniques that you can do, like using explosions and stuff, bangs, there's other techniques as well. But yeah, there's a few techniques around, but none of them are great.
Great. And then his second question is, how did you determine which sound absorption coefficient to use in the scale materials? And what is the error compared to that of the sound absorption coefficient of the actual in real life material?
So for the ground, I looked up some other people's measurements on absorption of materials that they'd used in scale modeling and found out that MDF unvarnished was similar to compacted ground with a 1 to 12 scale, and I just used that, partly because we don't really know what the ground conditions were like. I mean, ground absorption varies depending on whether it's, you know, compacted, waterlogged, or it's got lots of pores in it, and who knows what state it was in Stonehenge, to be honest. It must have been compacted at some time, but then they were digging loads of holes in it, so who knows. In terms of the people, yeah, we actually have a model scale rev room, a 1 to 10.
Trevor, we lost you again.
Hello, this must be very frustrating for people.
You're back.
I'm really sorry. I have no idea why it's decided to do that tonight. It's really annoying,
These
isn't it?
things happen.
So
Don't worry.
in the absorption of the people, we actually have a model scale rev room. So we measured the people, and then yeah, what you're comparing to is another problem. But yeah, we have a little model rev room.
Great. Then the next one from David Bianco, does the model pay consideration to the absorption of the ground?
It does, as I said, the uncertain. So when people talk about the uncertainty of the acoustics, the biggest uncertainty is probably the archaeology. Were other stones there? What were the real ground conditions? Were people in the centre of it? Because it will change the acoustics, and we just don't know. So actually, I think the scale modelling is fairly robust. We know what's wrong with it. What we don't know is some of the conditions that we're trying to model. It's just not knowable. So yeah, I think that's the problem.
Okay. Next one is from Lizette Victoria. We understand the model was done with a scale of 1 to 12 due to the real diffraction of the stones. Are you planning to test another scale that can be a little bit more accurate?
No, it was about 3 to 6 months to make that model in my spare time. I'm not planning to make another one. It was a huge amount of work because it's one of these things. It's a kind of project that doesn't get funded, so it's kind of like spare time project. Yeah, no.
And then her second question is, it isn't clear that the space has been used for a specific activity. However, I would like to know if there has been tests with instruments from the time to know what the musical range and not only the speech.
Yeah, I did do the next person asked about oralization of music, I noticed as well. So I did do some oralization of music. Now, the reason I don't play those examples is because I've got a limited frequency range I'm working in. I'm getting to the top of the 4 kilohertz octave band. I then interpolate what the 8 kilohertz octave band would be like. Now, in speech, you can get away with that because most of the speech is finished then. And so you don't really notice the modeling artifacts. But in music, you kind of more, I feel it's less certain what's happening at these high frequencies, which are obviously more important to music. So I have made some, but I tended to avoid it because I was just more nervous about whether it was right or wrong because I knew there's some interpolation going on. So I tended to use low frequency stuff for that reason. Yeah, in terms of music, what we know is there's not much evidence of musical instruments in Britain at that stage, but there is a flute being found not that far away. The best evidence is on Europe, so we definitely know the oldest musical instrument is like 40,000 years old. So definitely were things like bones with hollow bits and end-blown flutes, and of course singing. You know, you'd be hugely surprised if there wasn't singing there. So yeah, music. And what we can say with the reverberation time of 0.7 seconds is it would have improved music, because we know every sort of music is improved by reverberation as long as it's not excessive. So we probably assume it was improved, but it's not a very large reverberation time, so it's not going to be earth-shatteringly extra reverberant. But as a musician, playing in an anechoic chamber is horrible. Playing in a room with a bit of reverb is much nicer. So I'm sure it would have sounded better in there.
And I think you basically answered Fernando's questions. He is asking, have you tried creating organizations using music and echoing music, which might have been sung or played at Stonehenge? So basically address that. Question from Eliud Bonilla. Were you able to consider variations based on weather, windy days versus calm days? Thanks.
No, unfortunately, I mean, that's one thing we can't really do with the model at all. What I don't even know if we could, even if we just blew air across it, I don't think that'd be right. And yeah, so I think, yeah, winds causing sound refraction or temperature gradients causing sound refraction would have altered what goes on there. I guess it's only 30 meters across, so maybe not as, you know, it's not a vast distance, but we do know sound will carry more in certain weather conditions. But no, I have no sensible way of testing that, I'm afraid.
Great. And then from Richard Moscoso, I think you talked about the decision making on source positions. Dr. Cox, how do you determine the source positions? I mean, there was some decision based on possible uses from the archaeological interpretation of the place. You talked about a bit of that.
Yeah, so I think, so people talk about this stone which is lying down as being an altar stone. So we picked next to the altar stone, even though we don't really know if it's true or not. Some people have claimed focus at things in the middle where there's a focal point. So we start the source in the middle where there would be a focal point. Some people have claimed incorrectly that there's a whispering gallery effect in there. There's no way there's a whispering gallery effect. So we put it along the side. So we just kind of did that. And then we looked, well, what other sort of places haven't we tried? Let's try a few of those. So it was kind of a bit like that, really. There was no real, so there was logic in choosing the places, but to a certain extent, it was random. I mean, funnily enough, when the paper was submitted, someone said, and I don't know if anyone noticed this, it's probably quite a subtle point. Why did you test all the microphones in that corner and none down in this corner? And we never realized that. We tended to sample at one side. That was the bit which was nearest the door and nearest where the microphone preamp was. And it was just, it's such a pain to get leads around because you knock the stones over, and so we tended to test over there. So that wasn't a very good answer for the reviewers, but that was the honest answer. Some of it was convenience. And someone's asking about the speech, the speaker's characteristics for speech. So we had two sources we used, well, three actually. We had a low frequency source, which I didn't show. We had that sort of roughly omnidirectional in the horizontal plane source, but we also had the B&W source, which was just a single tweeter, which would be a bit more like a speech directivity. But to be honest, we never actually particularly, I've not looked at that to see, I've measured it, I've not looked to see how close it is to the voice. So things like reverberation time, you measure with the omnidirectional, so that result I was presenting with was with an omnidirectional source. But the oralization was done with that B&W loudspeaker because its directivity is a bit more like a real voice, but I don't know how close it is, I'd have to check.
Great. And I think this leaves time for just one last question. How to start researching archaeoacoustics seems like a very interdisciplinary field.
Yeah, so how I started off was I do quite a lot of public engagement work, which is maybe what I get known for. So I write books like Sonic Wonderland or the Soundbook. It's in America. And when I did a placement at New Scientist, which is the British equivalent of Scientific American. And they were very interested in me writing an article about archaeoacoustics. The guy was really fascinated by it. So I did a whole article about Stonehenge and other archaeological sites, looking at what science do we really and don't know in those places. And that included the measurements done by Rupert and Bruno of Stonehenge, Mary Hill. And that was actually the seed of thinking there's a technique, scale modeling, that has not been applied. But it took me probably about 5 years to actually then get some time to actually do it. But it's really, yeah, it's fascinating because it's interdisciplinary. And I would encourage, if you get into this area, it's really important to talk to others. So you'll notice on the paper we've got Susan Green, she's an archaeologist. I don't like seeing people, like archaeologists attempt to do acoustics when they do it wrong. And I'm sure archaeologists hates it when an acoustician tries to do archaeology and gets it wrong. So it's very important to collaborate.
Okay, that's all the questions we have. Thank you so much, Trevor. This was a very fulfilling, very interesting topic. We don't have a lot of archaeoacoustics presenters, so we're very honored to have you today. As we mentioned, this presentation was recorded. We will post it on our YouTube channel for everyone's reference. And I think that is it for all. Thanks again, Trevor.
Thanks, everyone.